Assalamualaikum everyone, I hope you all are doing well and taking good care of yourselves. This is your instructor Ali Faruqi and you're watching Science with Ali. So in today's class, we're going to be covering Le Chatelier's principle, which is about the position of equilibrium during a reversible reaction, and specifically how is the position of equilibrium affected by temperature, pressure and concentration. When we change these quantities, how is the position of equilibrium affected? So this is what we are going to be discussing in today's class. A quick recap of what we did in the last class. We discussed what reversible reactions are. We also discussed how initially the reaction is very fast in the forward reaction because only the reactants in the forward reaction are present in the mixture, and later on when the forward reaction has been moving on for a period of time, will the backward reaction kick in and the equilibrium will be established. We discussed what equilibrium was. Equilibrium was the state where the forward and backward reactions are going at exactly the same speed. And lastly, we discussed about the concentrations of the reactants and the products when the reaction is moving at equilibrium. A quick example of this which I gave you all was the production of ammonia plus hydrochloric acid from ammonium chloride, in which I told you all that if there is more ammonium chloride present in the reaction mixture, the equilibrium position will be towards the left because more ammonium chloride particles are present over here. And if there is more ammonia plus hydrochloric acid in the reaction mixture and less ammonium chloride, the equilibrium position will be lying to the right. Hence, we concluded that equilibrium refers to how many reactant particles there are compared to how many product particles there are when at equilibrium. So starting up with today's class, it is Le Chatelier's principle. So what do you mean by Le Chatelier's principle? Le Chatelier's principle is the idea that if you change the conditions of a reversible reaction, then the position of equilibrium will shift to counteract that change. For example, if you increase the temperature of an equilibrium mixture, the equilibrium mixture will do the complete opposite of that. So you just keep this in mind that whenever we do something, equilibrium will always try to do the opposite of that. It will always try to counteract that change. And so we can use this principle to predict what will happen when we change the conditions. To see what this means in practice, let's take a look at the reaction for the production of ammonia from nitrogen and hydrogen, and imagine that it was being done in a sealed system. Remember that I told you that equilibrium cannot be established until the reaction is being done in a closed system, right? So there's that. Now regarding this delta H, which is minus 92 kilojoules per mole, I discussed topic in my chemical energetics video, in which I told you all that a minus sign for the enthalpy change is for the forward reaction. So this forward reaction is exothermic, and so the backward reaction will automatically be endothermic, right? We discussed this in the last class. Now because the forward reaction was exothermic and the backward reaction is endothermic, now the forward reaction is endothermic, which means it releases energy to the surroundings. Now if I want to explain this to you a little bit more clearly, let's just say that my position of equilibrium lies in this manner. It lies over here right now, right? Now if I were to decrease the temperature of this reaction mixture, what will happen is that because the forward reaction is an exothermic reaction, which means it releases energy to the surroundings, it increases the temperature of the surroundings because it's exothermic reaction, what will happen is that the position of equilibrium will shift more towards the right in order to release the energy. Remember that the definition for Le Chatelier's principle tells us that the equilibrium mixture will always try to counteract that change that we do. For example, if we decrease the temperature in this case, the equilibrium mixture will try to increase it back again by favoring the forward reaction, right? This is what happens when we talk about temperature, which is controlling the heat. This is the factor 1, which is of Le Chatelier's principle. Now if we increase the temperature of this reaction mixture, if we added more heat, so if the forward reaction is exothermic, then obviously the backward reaction will be endothermic, and the endothermic process is the process in which the energy is absorbed from the surrounding, the temperature of the surrounding decreases because the reaction mixture absorbs the energy from the surroundings, and therefore equilibrium will shift to the left because the reaction mixture will try to counteract that change and decrease the temperature. Therefore it will favor the endothermic side, and therefore we will end up with more nitrogen and hydrogen than ammonia in the reaction mixture, right? Right, so this is a quick overview about what I just said. It is basically, you can just take a screenshot of this so you can remember it, or and jot it down so you can remember it as well. Now moving on to our second factor, which is pressure changes. We can also apply this concept to the pressure of our seed system, right? So there's a small concept that we need to remember, is that whenever we're talking about pressure, we will only consider the molecules or the compounds which are in gaseous state, because pressure in liquids and solids, because they are non-compressible, the solids and liquids are non-compressible, we cannot consider them when we are talking about equilibrium and pressure, right? So when we're talking about pressure changes, only we will consider the molecules and the compounds in the gaseous state. So if we look at this example over here, whenever there's a question regarding pressure, always look for the state symbols. There's a gas, this is a gas, and this is a gas. So we can apply this concept and we can consider all the compounds in this reaction. Now if I just counted the moles of the gases present in the reactants and the products, I will write down that there are 4 moles of gases in the reaction mixture in the reactant side, and there are only 2 moles of gas in the product side, right? Now let's just say that I increased the pressure of my reactant mixture, right? Now the concept is that the equilibrium in this case will shift to the right because less moles of gas are present in the reaction mixture on the product side, right? Now you may ask why. Because whenever we increase the pressure, to counteract that change, the equilibrium mixture will have to shift to the side with the least number of particles to overall reduce the pressure, right? If we increase the pressure, the equilibrium will go forward to reduce the pressure. It's basically the opposite of what we do. We discussed earlier. It counteracts. The Lechatier's principle is basically just the same thing. Now, because pressure is basically just a measure of how many particles there are per unit volume, to lower the pressure, the equilibrium will move to the side with the least number of molecules. Now if I decrease the pressure, right? So if I decrease the pressure, now the equilibrium mixture will go forward and try to increase the pressure again because I have decreased the pressure. Now how can it increase the pressure? It will move to the left because there are more moles of gas present on the left, and it is this 4 moles of gas that will increase the pressure back again if the equilibrium mixture moves to the left. I hope that's pretty clear. The main thing to remember from all this is that if we decrease the pressure, the equilibrium mixture will move to the left in this case because more moles of gas are present, and if we increase the pressure, the equilibrium mixture will move to the right because there are less moles of gas present in order to reduce the total net of the pressure involved in the equilibrium mixture, right? And remember this point is very important because if you mess up this, it's game over, right? Now the very last change that we need to look at is changes in concentration, right? Now what do you mean by concentration? Is basically the less and more number of ingredients, okay? Now if we look at it in this case, if we added more nitrogen to our reaction mixture, it would increase the concentration of nitrogen, right? So to oppose this change, the more nitrogen that we just added, the equilibrium will shift to the opposite side, which in this case is to the right, and forms more ammonia. Now you may ask why. If I explain this to you in writing, this is basically what it means, that if we added more nitrogen, then the equilibrium will shift to the right to decrease the concentration of nitrogen, because it is basically counteracting the change of adding more nitrogen. Now if we look at it in the opposite way, we will see that if we added more ammonia for example, right? So to shift the equilibrium, it will actually shift to the left to decrease the added concentration, the concentration of ammonia that we added. It increased the concentration, right? So to decrease that, it will move to the left. Now the same case would happen if I, for example, decrease the concentration of nitrogen instead of increasing, right? So when I decrease this concentration of nitrogen, the equilibrium mixture will shift to the left again to increase this nitrogen concentration back again, because when I decreased this nitrogen concentration, the equilibrium mixture was like, hey, wait, nitrogen is decreasing, we need to increase it again. So equilibrium mixture will shift to the left again to increase this nitrogen concentration, and therefore this wraps up our Le Chatelier's principle. The Chatelier's principle is very important in this reversible reactions topic. As always, if you have any questions regarding this video, you can always drop it down in the comment section down below. In the next class, we're going to be looking at Haber's process. So stay tuned for that video. As always, I hope you enjoy this video, and I will see you in the next class.